just definitely, I'm definitely gonna make sure that I do ask you a few things. Since I did take the time to do some thinking on part D of the NCD homework problem.
Let's start with some announcements. There's quite a bit actually happening today around, so I just wanted to make sure that people are aware of what's happening in the building. So first we have our assignment due tonight. We're doing day one of a review today. As we run out of stuff today, I will go back to the last few slides of interviewing, talking about job offers and how to evaluate offers. Then at between 12 and 2 down in the Catalyst lobby, there's the electrical engineering capstone presentations / interactions and events. They all have posters about the capstone projects that they've done. That is really cool, but joining them are all of my game dev students to talk about the games that they made. I do still have the big event planned on Friday for you to actually play them in a bit more detail, but this would allow you to wander around, ask some questions about the development of the games, interact with the developers. So there's that, and there will be food down there from 12 to 2 today. So even if you don't care about anything else, there's food. Let's see. What else do we have going on? We have our graphs project that's due next week. We have our exam on Friday. We're reviewing today and tomorrow. And that's just about it. There's not much class left to have announcements about, since we're just about done. This quarter flew by. I don't know if that was the case for you, but it feels like we just started about 2 weeks ago.
Yeah, it does feel a lot like that. Things have gone by just so fast. Actually, to be honest with you, for me, it feels like it's been a month since it all started. Not 3 yet, so.
Yeah.
It feels like I was born doing this and never ending small.
It's funny how both of those can be true at the same time. This quarter started yesterday, but also I've been doing computer science education for the last 7,000 years. I'm sure psychologists would have a field day with that.
Oh, yeah.
So I want to start just by asking, what questions do we have on the study guide? So I've pulled up the study guide and I can kind of go over my thoughts on these, but I just want to start with whatever questions that people have. What can I help clarify? What can I help give some practice on? And anything that I might be able to talk about how I would write some exam questions. What would I be targeting with these kinds of questions in order to help you prepare and make your study easy? So, NP completeness. Big topic.
Oh, yeah.
Yeah, NP completeness is a big part of this.
And if we go over that today, if that right, that helps our home.
That does. That's true. Request for Ford Fulkerson and Edmunds Carp online. That's a good idea as well. If you just come up with a graph and we could trace one or the other.
I should have thought about that when I mentioned it. Hope we had enough time to make some problems.
Yeah, I don't have a ton prepared for problems. I can come up with an arbitrary graph that we can do for Fulkerson and Edmunds Carp on. That's not one that really needs a ton of preparation. You can just make a particular flow network and that work. But yeah, I guess we could just quickly go over some of these. So I'm not targeting much with all pairs shortest path. The reason is the actual implementation of that is on your assignment. So the only thing that I could reasonably target at this is why we would use Floyd Warshall and just be able to explain how it works at a high level. I'm not going to have you trace that because it's 3-dimensional. And I don't know about all of you, but I have the artistic ability of a second grader. And if I were asked to draw out something 3-dimensional and trace something 3-dimensional on an exam, I might as well just shred the exam right then and there. It's not going to go well. So I'm not going to have you do that. The outcome for that is on the assignment, but just know the algorithm at a reasonably high level. Then we had maximum flow. So just the components of that, what was an augmenting path, what was a residual network, what's an anti-parallel edge, be able to apply all of those ideas to both the Ford-Wilkerson algorithm and the Edmonds-Karp algorithm.
Go over some of that terminology again.
Yeah.
Refresh it.
Absolutely. So let's start with an augmenting path. This is what we use when we find a simple path from source to sink. That augmenting path just says that some amount of material can flow along this path. We found the constraint of what is the smallest edge weight along that simple path, and then we subtracted it from a forward-facing edge and added it to the backwards-facing edge to say we're going to put that much flow down that simple path. So the augmenting path is just that path from source to sink.
I guess my
Yeah.
question on is like, it sounds like it's just a, what makes an augmenting path? Question, why are they using because that's the whole point, you're finding.
Yeah.
So.
Yeah, the why they use it, it's really just what is the point of an augmenting path? It's finding some path from source to sink that some additional flow could go down.
Wow.
To be able to iteratively work to maximize the flow along between source and sink.
So it has to be iterative.
Yeah, it's for the current iteration, find that. Just because you found one doesn't mean others don't exist. So when you create the residual network out of that, which we'll cover in just a second, when you create that residual network, then you can find another augmenting flow, create the residual network from that, and you loop the finding an augmenting path, calculate the residual network until you can no longer find an augmenting path, and that will maximize the flow from source to sink. So we also found as reasoning why we use Edmonds-Karp, what happens if we randomly select an augmenting path. If we do that, then we get a bad worst case guarantee on the number of iterations of augmenting path residual network that we go down. The worst case for that was big O of the size of the flow, which is not good. So the optimization that Edmonds-Karp uses is to find the shortest path by number of edges, not caring about the edge weights. If we use breadth first search for that, then we can guarantee convergence faster than the total amount of flow. So the residual network is just the network that's left over once we find that augmenting path and send an amount of flow down that augmenting path that is the capacity of that path, the smallest edge weight on that path from source to sink. And Ford-Wilkerson just said arbitrarily pick an augmenting path, and Edmonds-Karp further specified that we will pick the augmenting path with the fewest edges between source and sink. So I will circle back to this either today or tomorrow. We'll figure out, depending on how the class feels about how we should prioritize this. I would like to go over an example of this. I'll kind of do a high level pass first and then go back and say, what do we want to get examples of?
And see really.
Yeah, anti-parallel edges are the ones where we have an edge going from U to V and an anti-parallel edge going from V to U. The anti-parallel edge represented the amount of flow that's currently in use, and the regular edge is the amount of flow that we have available. So that way if we can find a path from source to sink, some of that's going to be in use as the anti-parallel edge, but that means that there is a path with some amount of flow from source to sink with those forward-facing edges moving from source to sink. That's why we don't allow for otherwise anti-parallel edges. We can't have the example that we saw on the slides was some available flow between two nodes that, you know, we could have some flow that could go in this direction and some flow that could go in that direction. That's not possible in this situation. We needed to allow for a third edge and basically triangulate with a dummy edge to be able to model that. And then we could have that. And we can create anti-parallel edges for all three of those edges to say how much of this flow is used. But I use the analogy of a ghost town to say that we're just going to ship it between some arbitrary third location that's not actually there. Represent that idea. All right, NP completeness. I get the sense that this is probably the big category of confusions, clarifications, and just a desire for more practice. So things I'd like you to know or be aware of, just be able to describe why exponential complexity problems are intractable. In the motivation slide for that, drew out how exponential growth happens. What is 2 to the 10th, 2 to the 20th, 2 to the 30th? Be able to just have an intuitive idea of why that doesn't scale well, regardless of the base, regardless of how small that exponent is. Exponential growth is wild, truly wild in its growth. See, did I use the paper folding example in here already?
That might be familiar. Yep, I think I'm also seeing this question like a G. Why is the class P considered to be tractable, even though large polynomial values like n to the 100
Yeah,
are intractable?
yeah.
Yeah, I think that makes some sense. Alright, I should be a lot more careful.
So just have an idea or an intuitive idea of why that is, just so you can add that to answers and explanations of questions that I'm probably not going to be targeting exactly this question, but something where this might be part of an answer for why a particular NP complete, describing something related to NP completeness. If you could rope in an argument about why exponential complexity is intractable for large inputs, then it will make your answer a lot stronger.
So, kind of think you may answer this if we think of polynomial in a more general way. Got it. 100.
Usually, so when we find a polynomial time solution for something, there are many more optimization tools that are available. So we can remove something that was n to the 100th and cut that in half to make that the exponent in half. Now we have an n to the 50th solution. Then we can find another optimization, and so very few things actually run at n to the 100th. It would be pretty intractable to have something at n to the 100th, but we have a lot more tools available to us mathematically to look at and analyze and optimize polynomial problems rather than exponential problems. Yeah, very little in practice actually has a particularly high exponent, constant exponent in a polynomial problem.
We have more tools. Polynomial problems.
We don't really have, so exponential maps to things like combinatorics, whereas something that's polynomial maps directly onto loops, something that we have programmatically. So we can take any compiler related optimization and apply that to, can we make this loop simpler? Can we find an equivalent loop that, can we find a loop in here that we don't need, that isn't doing anything for us, and can we optimize that whenever we don't need that loop? Whereas combinatorics, when can we skip and not look at particular combinations of things? That's a lot harder to be able to justify. We can't look directly at the syntax of a program and say, can we map this differently onto assembly instructions? Can we, stuff like that. It feeds into the tools that we already have and are already written and are mathematically sound. Would be the best way I think that I can describe that with my own understanding. That's a really good question. All right, the next thing we talked about, what are the classes of P, NP, NP complete, and NP hard? What do each of those represent? And then also how do they relate to each other? So P was the class of languages that are deterministically solvable in polynomial time. Deterministically, we mean we could write a program for it. NP were non-deterministically solvable in polynomial time or verifiable in polynomial time, or solvable with infinite parallelism in polynomial time. All of those are equivalent.
Not P is basically what it states, not P.
Well, we don't know necessarily. The whole P equals NP question is, are these classes exactly the same?
Yeah, that's,
Are those sets containing the exact same set of algorithms? And we have no proof for or against that.
yeah,
So right now we have two different definitions and an open problem of, are these equivalent? My best guess is no, they're not equivalent. And we have a lot of assumptions out there that rely on them not being equivalent.
that's exactly what I was thinking too.
So with non-determinism, we allow for that level of infinite parallelism. If we had basically infinite compute power, then we could map a non-deterministic problem onto a deterministic one. We'd be able to do the exponentially large search in much less time. So it becomes closer and closer to equivalent. So the question is, as the power of hardware accelerates, it approaches a limit, do these problems become the same in complexity? I think is how I tend to try to understand it.
Yeah.
Right now, we have limitations with our hardware. We will probably forever have limitations with our hardware. But infinite parallelism just says, if we always had more hardware to throw problems at, how are these classes of languages the same?
We had hardware. It wouldn't make an exponential problem not an exponential problem, it just make it.
Right, so it would still be exponential, but it would be solvable in that the reason it's exponential is we need an exponential number of threads running for something like cracking a password. The only reason is I have to search one at a time, or as many threads as I have at a time. And the number of threads I have is a constant. So I'm dividing an exponential problem by a constant. But as soon as that scales to infinity, then I have the equivalent of an exponential number of cores, an exponential number of possible threads. So I can take an exponential size problem and say, do it all at the same time.
Right. Get why that makes it possible now. Calls.
It makes it constant because we can take all of those exponential number of problems and run them at the same time. So basically it becomes O1. Because we can, as long as we can define the problem in terms of mapping subproblems onto threads, then we'd be able to verify the solution. We'd be able to search through the problem and find an answer extremely quickly.
It's a semantic that.
Yeah.
It's still, the problem itself is still an exponential problem.
Right.
So it would still be NP, just by definition, wouldn't it?
It would still be NP, but then it would also be solvable in polynomial time, deterministically, by saying that we can now deterministically feed to our exponential number of threads this exponential problem, where in a constant amount of time, we have a solution and have gone through an exponential number of subproblems. It's about how much time elapses, not the number of threads that are required. Right now, with a limited number of threads, it's going to take an exponential amount of time. But if we had an exponential number of threads, then it would take a constant amount. So the time becomes polynomial, even though the problem definition, the number of subproblems we have is still exponential. At least I think that's the best that I can think of. I'm sure there's a better theoretical way of explaining that, but at least that's how I personally understand it. But it leads to some deep thoughts about just the nature of computation. It is definitely philosophical, but at the same time, it kind of leads the it leads research forward in what are we trying to do? What should we be targeting with our research? What is going to be the next big breakthrough? Where should we be spending our money? Where should we be spending our time? Less so, does this help us solve a problem today? Other thoughts on that? It's a big question, and it's a big open question. But it keeps theoretical computer scientists up at night. That's why they don't get any sleep.
I'm at least understanding a little bit better now. Yeah, let's see,
So that was P and NP.
yeah, let's see, that P equals NP. Problem because does P have the same complexity or is NP or is it speed? You know, sorry, I'm just trying to understand the basics of it all.
Yeah.
I also apologize, I have not been hearing everything. But I pulled up some PowerPoints on my laptop just to make sure I was understanding and keeping up with class.
So what was NP hard?
Hard. Is it that, wasn't it that set of non-deterministic? No, actually, I think. Now, wasn't it one that set of NP problems that is only solvable in exponential time and no, I'm gonna double check myself.
Yeah, that was NP complete.
Yeah,
It's a common confusion between NP complete and NP hard.
Looking through it now.
Well, correct, I think that NP hard is that is NP complete and also is also intractable and
Yeah, there are NP hard problems that aren't necessarily proven to be NP complete.
Okay.
Yeah,
NP hard is every language in NP is polynomial, time reducible to the target.
yeah.
Nice, beat me to it.
Yeah, right off the slide, but we can reduce any problem that is in NP to the target problem in polynomial time. So usually this is a first step to proving that something is NP complete, because then we need to be able to reduce it to a target problem that is also NP complete to be able to show that if we could solve one problem, then we could solve the other. But there are more NP hard problems than there are NP complete problems.
an NP hard problem is a problem that can be reduced to an NP complete problem.
To every NP problem, basically any problem that is polynomial time verifiable, there is a polynomial time conversion algorithm to that NP hard problem.
That makes sense.
It's how we add problems to NP, basically.
Okay, so yeah, it says here, oh yeah.
Then NP complete is a set of problems that we don't have. They're basically shown to, as far as we know, not be in P. We haven't proven that they aren't in P, but no one has proven that any of these problems are in P. So if one of them is in P, then all of them are in P. Because we have that polynomial time reduction between this class of problems. But everything in NP, some of those are provable to be in P. So there are some NP hard problems that are reducible. You can reduce down to that target problem from one that is both in P and in NP, and we can show them.
Well, I don't know how to sound.
I know, I hate it. In P and NP are different, which is terrible.
I think the deterministic part helps it tell on part because P is deterministically solvable and P is non-deterministically solvable.
Yeah. I feel like I should give someone some extra credit for coming up with the absolute worst tongue twister you can with in P and NP and something that makes actual sense.
Regardless.
Someone's gonna focus on that too much for the rest of class. I'm sorry in advance. So the P equals NP question was just, are these classes of languages the same? We can't prove it, we can't disprove it. We've been trying for decades. We have an assumption that P is not equal to NP. So if anyone ever solves this problem and proves that P is equal to NP, start digging. You need a bunker now. We covered non-determinism, just what non-determined is, be able to describe it again at a high level, give an example of it. I think that's probably good for just the idea of non-determinism, but the idea of non-determinism is baked into the entirety of NP, NP complete, and NP hard. So just an understanding of non-determinism is a basic necessity for understanding those classes of algorithms.
But yeah, should we have a list maybe on our sheet of the problems that we are NP complete?
That is a good question. The reason I would say, so I'm kind of split there on how or why that would be useful to you. I will not have you doing a reduction, which is when I would say absolutely yes, they should be on there so that you know what you could reduce a target problem to. If I wrote a question like that, the easiest question that I can imagine with a reduction would be at least a 30-minute task, which would mean that that is the only thing I'm covering from NP completeness. And I hope everyone can do it in half an hour, because otherwise you have to decide between fleshing out that problem or finishing the rest of the exam.
Yeah.
I don't want to put you in that position. So I don't think I will be asking you do a reduction. On the other hand, I might have you linking some problems together and just intuitively saying, is this solvable? Is this problem solvable? Is this problem not solvable? Be able to justify why or why not. And so having a list of NP complete problems might give you some ideas about, it's reasonably similar to this other problem, and here is why I think that is. It's not a full reduction proof, but it at least gives you an idea of where to throw an argument forward, how to put an argument
That's
forward.
kind of where I was. So
Yeah,
are there,
but it shouldn't be necessary. I won't try to pick a problem that requires you to know the existence of another problem in order to be able to solve it. Whenever possible, I want to give people multiple avenues to come up with a solution that show that you understand it. I will never be looking for exactly one specific train of thought. Because I don't believe that computer science is quite that mathematical. It's not like there's one right answer and an infinite number of wrong answers. There are frequently multiple ways to understand things. I don't want to pigeonhole you into describing something only the way that I'm looking for.
are there limited list of ones that we've gone over that we should be familiar with?
In general, it's worth knowing the ones that were in that diagram that I put on the slides that are in the book. But I will only ask questions that rely on the knowledge of the ones that we've covered in class. Both the ones in the NP completeness slides and the ones in the approximation algorithm slides.
All right, we're already over halfway through this class already. Are we gonna go over the problems?
We'll either get to that at the end of class today, or we will say that we want to go over problems tomorrow. We'll see how we feel about that once we're through this, depending on also how people want to.
Thank you for the honesty, this is why I asked these questions.
It depends on what is the best use of people's time. Anyone at any point can just raise your hand and say, let's take a vote. Do we want to go over an example of Ford Fulkerson or Edmund Scarp right now? Let's ask that. Show of hands, is that the best use of people's time right now? Feel free to say yes, feel free to say no.
I don't fully remember though, so yes.
I would like to make sure that I at least brushed up on.
I definitely want to go over them, but we have time.
Yeah, we definitely are gonna have time in one day or the other, but if this gives you an extra day to study what we go over, then it's the better use of time to do today than tomorrow. I get quite a few yes votes here, a couple of yeses remotely, as well as about 4 hands here. Would anyone rather go through the rest of this and kind of talk at a higher level the way that we have? Show of hands for that. Two, 3.5.
I'm sorry, what?
4, 4.5. A couple other. It's So we seem to be very evenly split on this. I'm gonna make the executive decision that it's easier to talk about the high level and give me a little bit more time to prep examples that are meaningful, rather than potentially throw something up on the board, realize that it's not the best example halfway through it, and have to describe to people why it is the not the best example and why you should come up with another example, or I should. So I'm gonna do that. We'll see how much time we have at the end of class, and that'll be the first thing that I cycle back around to, depending on how much time. Regardless, we certainly have enough time tomorrow to go through at least 2 examples of that, as well as anything else that people tell me they'd like me to prepare. That fair? Does that work for people? Okay. So the next problem here was proving that a first problem is NP complete.
Yeah.
So that was the difficult, very difficult first proof that we did. And what was different about that? What did we need to do for that first proof?
We needed to prove, we did need to prove it, like that it was, let's see, that it was, that the algorithm was in NP and that it was NP hard, which
Yes.
basically means it was non-deterministic and only solvable in exponential time, right?
Yeah, so you can imagine that there's this entire class of algorithms that is NP. And we have this target problem down here, and we want to be able to show that this problem is NP complete. It means that we need to prove that we can reduce every single problem in NP down into this problem. Doesn't matter where these originate from, every single problem in NP must be polynomial time reducible to that target problem. And that is difficult to do because we need to generally argue that regardless of the structure of this problem, it's polynomial time reducible, and that's disgusting. To add a second problem to NP complete, we could go through this exact process again and say, well, this is polynomial time reducible from everything here. Or we could say it's polynomial time reducible to the one problem we just added. If we do that, this is much less work than all of this. Because if this problem is polynomial time reducible from every problem in NP, then so is this. We go through this conversion process and then this conversion process, and we're there. So as we start to grow this set of algorithms that are polynomial time reducible from other problems that are, we start to get this class of algorithms that, yes, they're also in NP. This is a subset of that. But it's one where we can start to add to this with a much simpler process. We just have to show a polynomial time reduction to a single problem in that class, which indirectly shows that it's polynomial time reducible from everything in it.
Okay.
So we start building this class, NP complete. And if we can solve one of these problems in polynomial time, we can solve all of them because they're all convertible between each other in polynomial time. That's the big idea between how do we prove the first problem is NP complete, how do we prove that the next problem is NP complete, given that we have some problems in this set of NP.
That's what's. Problem.
Yeah. Yeah, that's how we add a new problem to that. That's how we define a new problem that is intractable, but would be tractable if any of these problems are tractable. To the best of our knowledge, none of these are solvable in reasonable, feasible time.
Yeah.
But if one of them is, then all of them are. Which is a very interesting thing to state.
Yeah, so I get it. Yeah, that the reduction proof is really complicated. Still, and barely understand it myself, to be honest.
That's why
That's,
I present it to you, but don't ask you to be able to reproduce it, or don't ask you to be able to extend that to something that is new. I would expect that out of a graduate level out of class. But at the undergraduate level, I think understanding how and why is more important than being able to reproduce.
well, production on proofs like that are not exactly the most unfamiliar thing to me. It's just been a while.
It's a bit of a challenge. It's a lot of a challenge to throw on an exam and expect that everyone can get close or get there.
Smart.
So then we've already somewhat addressed why is P considered to be tractable for large polynomial values. It's just that we have more tools. Then just be able to explain why the problems that we've covered so far. This is the set of NP-complete algorithms between the two slide decks on NP-completeness and approximation algorithms that we have discussed. We talked about circuit satisfiability, Boolean formula satisfiability, vertex cover, traveling salesman, subset sum. That should be a comment on a period. But since we've gone over all of them, just be able to give a reason why each of those are NP complete, either through tying them together in ways that we did, or just a reasonable, intuitive argument.
Well,
That's going to be necessary for some problem on the exam in some capacity. I'm not going to target this. This is, again, not something I'm going to target directly, but something that would be the reason why you have a complete answer to a differently targeted question. I don't like questions that are quite that specific, because it leads to memorization. The tool on the outside of that of how do you determine whether something is NP complete? How do you understand that something is NP complete? That's what I target. Yeah.
Sorry for the random question. What are we doing on Monday?
Right. We technically have a meeting on Monday, don't we?
we do. Well, actually, wait, no,
Or is that just winter?
This is, no, no.
Or is Monday is that supposed to be our finals period?
Our finals period is supposed to be on
Then it's
Tuesday,
Monday's finals.
we started at 9.
We're
And
doing
go-
nothing next week. I'll make that easy on you. We're doing nothing next week.
And here I thought you were gonna pull out your magic cards during the final day, we all play magic.
I can say that I would be here and be up for that if anyone wants to do that, but I'm certainly not going to require that people be here on a random day during finals week where I force people to do something that's not related to the class.
We all have to play that.
Are you telling me that magic is not just algorithms?
It is. It is tangentially related, but not in a way that
Very related.
it is. If you're good at thinking about algorithms, that does certainly translate to being good at magic. All right, the last category here was our approximation algorithms. Why is it important to be able, that's not the last, we still have the cumulative ones to cover. Why is it important to be able to approximate NP-complete problems? Since it's not solvable, we want to be able to come up with, we need something that works in a reasonable amount of time, so we need to be able to quantify how the trade-off between the time that it takes for the algorithm to complete and how close to the optimal answer it is. That trade-off can be prioritized differently, where you need something that runs very fast and you're okay with an answer that's wildly different from the optimal answer, or you can take a bit more time and get closer to the optimal answer. In a lot of cases, you have that kind of freedom and those kinds of options. We presented a few approximation algorithms for a few NP-complete problems, but there's nothing that says that that's the best we can do, or that is the best point in that trade-off for that particular problem. There may be other approximation algorithms that you could think of that prioritize those two variables differently. Imagine that you're out in the world and need to solve an NP-complete problem. We talked about some of the options that exist for that. What questions would you ask? On the slide, there were things like, What is the size of the problem? We can just brute force it if the size of the problem is small enough. Doesn't matter that it's exponential complexity. We could invent an approximation algorithm or use an existing approximation algorithm, and then you would need to answer the question of to what extent are we prioritizing those variables with that approximation algorithm? Should we find a different prioritization? So that's what an approximation algorithm trades off.
Two options, brute force or approximation.
That's basically, there was one more on the slide deck that I don't recall off the top of my head what it was. Those are the two that are probably the most useful or beneficial. There are constraints that you can add as well that you can, yeah, that's what it was. You can constrain the problem in such a way or recognize certain constraints on the problem that make it more solvable or in certain special cases. So if you recognize that what you need to solve is a special case of an NP-complete problem, then you add constraints to the problem and do some constraint satisfiability. If you want to see more about constraint satisfiability, take my AI fundamentals course in the fall. That only has 7 people in it right now. We need more people in that class. It counts as a CSCD 400 level elective, even though it's listed under cyber.
That's why I couldn't find it. Okay.
Yeah, there are a couple options next year that are going to be treated more like computer science classes, even though they're listed under cyber. So if you're looking for an elective to take, browse the cyber electives.
Wow.
They count, and sometimes they're taught by CS professors that are very interested in a CS related class. So if that intrigues you,
I haven't even asked about
need more people in there.
that.
Intriguing, but is it easy?
It's one of my classes. I'll leave it at that.
It's easy as
It's harder than this class, but probably slightly easier than compilers.
that's about.
It's enough of me for one quarter. After taking 2 classes for me this quarter, it's like I've had it.
A lot.
It is.
So what I'm hearing is you recommend taking both your AI fundamentals and compiling.
There's a reason why compilers is offered in the winter as well.
Well, it's available in fall as well.
Let's see.
So last couple of points of this one, how does one quantify an approximation algorithm's efficiency? We didn't really go over a method for that, but just be ready to talk about that kind of at a higher level, or the difference between quantifying the efficiency of an algorithm that is deterministically polynomial time and an approximation algorithm. What are you looking at with that efficiency?
What?
Well,
Answer that?
that's a great question.
Yeah.
To be honest, I think looking through the problem and looking through like whatever code we were.
Yeah. So for an algorithm that's just in P, that is deterministically polynomial solvable, the only variable is its running time. It will complete optimally in that amount of time. The approximation algorithm has those 2 variables. How long does it take to complete? And what are the error bars on the optimal solution? So that's the difference in quantifying them, is that there's an extra variable to account for and trade off in deciding what approximation algorithm to use and how good it is. We need to quantify both of those with an approximation algorithm. And considerations that are necessary to formalize an approximation algorithm. What do we go through in order to turn an approximation algorithm into one that's actually used? And that really means that we need to do that quantifying. We need to find that theoretical bound on what is the worst case for how much worse it is than the optimal solution, as well as the worst case for how long it will take to run. Once you have that, then you have a formal approximation algorithm that you can publish. Last, we have a set of cumulative questions. Again, I will not be asking you questions that I should have asked you on an earlier exam. So these cumulative questions are all high-level tying things together kinds of questions. There will not be specific questions on anything from a prior study guide. So Questions like at a high level, why is the study of algorithmic efficiency important? We talked about that in a bunch of different domains. We talked about that from analyzing recursive algorithms, from the different tools that we learned about with dynamic programming and greedy algorithms. So why is it necessary at a high level? We talked about it theoretically with these language classes of P, NP, NP complete, NP hard. What theoretical questions can be asked and answered by the study of algorithmic efficiency? What practical questions can be asked or answered? How are you using this on a daily basis in a real job? How are you using this to think about moving the field as a whole forward? Then the tools for solving problems efficiently. So just know of dynamic programming, greedy, etc. I may ask you or give you a problem, kind of like the Bonnie and Clyde problems on the current homework, that says, what is the best solution that you can come up with for this problem? Argue whether this is worst case exponential and probably NP complete, whether it's polynomial time but best solvable with dynamic programming. Does a greedy assumption work here? I won't be targeting the knowledge of dynamic programming or greedy, but I might have you justify how you would solve that problem. I won't have you go through and solve that problem, but just recognizing what tools you have available, which tools you can pick in order to solve this problem. This shows true mastery of this content, when you can pick the appropriate tool to solve a problem you haven't seen before. How could we determine and quantify bottleneck structures and algorithms in a larger scale project? So imagine that you have a large amount of code and you want to figure out what is the order of this code. Think back to the first couple of weeks of this course when we were analyzing small scale methods and figuring out the running time of that method. But now imagine that instead of analyzing a method, we're analyzing a large scale program. And now we need to break this down into what are the methods, how frequently are the methods called, what is the bottleneck here? If we removed one of these methods, which one changes the runtime of the algorithm? So just being able to analyze and look at and find places where we could find better efficiency. Is the bottleneck here the fact that we're using selection sort instead of a more efficient sort? The entire program would run an n log n if we took this quadratic sort and we replaced it with a log linear sort, something like that. Yeah.
Is there any other way to do it other than go through the whole program before it?
Yeah, that's not really another way to do it. It's just at this point you have the tools to be able to analyze a recursive method in the context of a larger program and figure out what is the complexity of this method. How many times is it being called? Where is it being called from? So you might be able to start to take this idea and spread it out into a larger scale analysis of a larger scoped project than just the small code pieces that we had earlier on in class. And that's what you're going to be tasked to do out in the real world, is determine the large scale efficiency of a solution, not just a method within the solution, or that is a part of that problem. But at this point, you should be ready to analyze things. So it's not something that we've specifically covered, but it's also something that just uses the tools that we have talked about. The second part of that is optimizing the efficiency of a large project by looking at its components. This would be like saying we should swap out this sort for a more efficient sort. If this sort is in the middle of a cubic algorithm, using a quadratic sort versus a log linear sort doesn't matter that much because the bottleneck is elsewhere. It's not going to meaningfully increase the amount of time that it takes for this program to run. But if it is the bottleneck, then it is something that we should absolutely find and fix because it's going to be the reason it takes as long as it does to run. Much bigger scoped problem. How can we use solutions to problems we've seen before to help us solve new problems? This is something that we've seen a few times throughout the course, but in general, I may throw a problem at you that is similar to a problem that we've seen before, and just being able to apply your knowledge of one problem, solve another.
Okay.
And then another larger scale, how can we determine that a system is performing efficiently enough? This can either be based on client specifications or adhering to certain specifications. I might ask you, does this code adhere to these requirements? These runtime requirements, which would again have you looking at the components and how the methods play together to determine something like, do we meet the specifications based on the code that is in front of you? And maybe that code uses dynamic programming. Maybe that code uses recursion. But I'm not targeting those with the question. It's a larger scale. Can you analyze a larger scoped problem and map it to requirements and specifications? Stuff like that. How are we doing? For any further last minute questions, since we're basically out of time on anything from these last few sections, hopefully that helps you get a sense of what I'm targeting with these kinds of questions and what I might ask you to be able to do. If you have any questions about how to take this and study for it, feel free to let me know. I'm talking in office hours. I'd be happy to talk to you about how to think about this, how to move forward with it, but
At least understand a lot of it, but I think get distracted. I thought, yeah, it's not